If your neighbors feel random, your embeddings are trained for your task. Fix it with contrastive loss. By the end, you will understand how to train embeddings that pull true matches close and push irrelevant items away, so Retrieval actually finds useful neighbors. I'm Professor Pi, teaching AI foundations with simple Python. Contrastive learning for Retrieval solves a common problem. You build vectors for queries and documents, but raw vectors often put unrelated items near each other. That kills search relevance. Contrastive learning changes what the model cares about by showing examples of anchors, true positives, and negatives, and teaching the encoder to rearrange space so positives sit near anchors and negatives sit far away. At a high level, contrastive learning for Retrieval is about shaping distances. Imagine a couple of sentence pairs where one is a paraphrase and one is unrelated. Success means the paraphrase has a high similarity to the anchor, and the unrelated one has low similarity. The method is strong on small to medium datasets and is tidy to scale when you add a mining step to pick the most confusing negatives. We will build a small toy workflow that demonstrates the idea end to end. You will see encoding, scoring with cosine similarity, a margin-style contrastive loss, simple training with stochastic gradient descent, a hardest negative mining pass, and finally a nearest neighbor retrieval step. None of this needs exotic APIs. Keep the example small so you can follow every choice. Now we will encode toy pairs and inspect cosine scores. This snippet uses PyTorch to encode toy pairs and measure cosine similarity. It builds a simple encoder that maps each input to a vector, then normalizes those vectors so length doesn't change the score. The core lines first create anchor and positive tensors, then run them through the encoder to get embeddings, and finally compute cosine similarity, which measures the angle between vectors and ranges from -1 to 1. Normalization matters because cosine cares about direction, not magnitude. If you skip normalization, the network can cheat by inflating norms. This snippet shows the baseline numbers and a quick sanity check that true pairs are more similar than random pairs. Next, we turn those scores into a loss that separates positives from negatives. This example computes a PyTorch contrastive margin loss from cosine scores. It takes the cosine between anchor and positive and between anchor and negative and applies a margin that enforces a gap. The loss pushes the positive similarity up and pulls the negative similarity down until the negative is at least margin units worse than the positive. Important lines show computing the difference between positive and negative scores, subtracting the margin, and then applying a hinge-style clamp, so only violations contribute. The margin hyperparameter controls how strict the separation is. A larger margin demands bigger gaps and can force stronger reshaping of the space, but may slow convergence on small data. Now we will run an optimizer to adjust the encoder parameters. This code trains the PyTorch Siamese encoder with stochastic gradient descent to reduce contrastive loss. It sets up a tiny training loop where each batch computes embeddings for anchors, positives, and negatives, computes the margin loss we just described, backpropagates gradients, and steps the stochastic gradient descent optimizer. Key lines show zeroing gradients, calling backward on the loss, and stepping the optimizer. The learning rate on the optimizer is the main knob here. Higher values speed learning, but risk instability. Lower values require more steps. In practice, you watch loss and retrieval behavior rather than loss alone to decide when training is good enough. Next, we will pick tougher negatives, so training focuses on real mistakes. This snippet mines the hardest negative in PyTorch by scoring candidates against the anchor. It computes cosine scores between the anchor and a set of candidate negatives, then selects the one with the highest score among negatives, the one the model currently confuses most with the positive. The code shows a scoring pass over candidates, an argmax to pick the hardest index, and then reuses that example in the loss calculation. Hard negative mining makes each training step informative because the model sees the most confusing counterexamples. Be careful. If you always pick the single hardest negative, you can overfit to rare outliers, so a balanced strategy or periodic refresh works better. Now that the encoder is trained, we will run a simple retrieval query. This example retrieves the nearest neighbor using the trained PyTorch encoder. It encodes a query, encodes all torpus items, computes cosine similarities between the query vector and each corpus vector, and returns the index with the highest similarity. The important lines perform a batch encode for the corpus to avoid repeating work, then a single similarity pass and an argmax for the best neighbor. In small setups, you can do brute force similarity. For larger collections, you swap in an approximate nearest neighbor index. But the retrieval behavior you see here is the direct measure of how well contrastive training arranged the space. Map to a real project. Replace the toy corpus with your documents. Use mini batches that include one positive and several sampled negatives, and regularly mine hard negatives from a larger candidate pool. This pattern moves you from a classroom demo to a practical retrieval engine. Recap. Contrastive learning trains encoders by pulling positives close and pushing negatives away. Use it when you need task-specific retrieval quality and unlabeled or weakly labeled pairs. Caveat: aggressive mining or an oversized margin can overfit or destabilize training. Next step, tune the margin hyperparameter and the hard negative sampling frequency. Then measure retrieval accuracy on a held-out query set. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.